Okay, so last week I decided not to use the wireless mic, well, because it wasn't here. This week the wireless mic is here, but I'm going to not use it. Anybody have a problem hearing me? No. Awesome. Okay, so this is the third lecture. So last time we talked a bit about electromagnetism, or the first time we talked about special relativity, we talked about quantum mechanics, so we sort of got those things out of the way. And now the rest of the series can be divided sort of into two parts. There's 3 parts that are going to talk about particle physics, and then 4 parts after that that will talk about gravity and string theory. So, well, I wanted to have sort of 3 lectures and some things about particle physics, and I thought it'd be nice to start with the most exciting thing that we're most excited about for particle physics right now, which is the Higgs boson. So today's lecture is all about why we need the Higgs boson, and then next time we'll talk about the standard model, some of the problems of the standard model, and why we think, despite the fact that people have been looking for problems in the standard model for 30 years, why we think the LHC should succeed. And then I'll have a whole lecture on supersymmetry before we go into the rest of this stuff, which hopefully will be fun, although there's some questions. So last time I threw this up at the end, I was doing it very quickly because I was running short on time. Last time we talked about quantum mechanics, and we ended talking about the quantum theory that describes electromagnetism and how electrons talk to electromagnetism, and that quantum theory was quantum electrodynamics. And I wrote this thing up here. This thing is called, this is Lagrangian, and if you're talking to a particle theorist and you want to tell them what your theory is, this is what you do. You give them something like this, and I pointed out that there are basically 4 important ingredients here. You have to say sort of, well, 3 really. You have to say what the particles are. So we have to say there's an electron, we have to say there's a photon. You should say what the charge of the photon is, so how strong the electromagnetic field is. But we pointed out that there was another parameter sitting in here, which is the mass of the electron. And quantum electrodynamics, which these people won a Nobel Prize for, is perfectly happy to have a massive electron with no problem. There's no problem with mass. We don't have to invoke anything like a Higgs boson in order to describe electromagnetism. And QED is, in some sense, the most precisely tested really model of anything in nature. We heard a nice colloquium in the physics department this week where Jerry Gabriels came and told us about the measurement of the anomalous moment of the electron, which is now incredible to hear the technology that they have to do that. You're measuring it to 1 part in something like 10 to the minus 13 or something ridiculous, and finding agreement with theories. It's very nice. So we have mass without Higgs, wild to fuss, and well, quantum electrodynamics is fine, giving mass to particles without a Higgs boson, but the nuclear interactions aren't. And so in some sense, this lecture is really a story about the nuclear interactions, which we don't experience in our everyday life, which is why the fact that you might need something like a Higgs boson is not very intuitive. We think mass is just something that's there. We don't see any reason to have some new particle to give mass to everything, because in our everyday life we pretty much experience electromagnetism and we experience gravity. We don't experience the nuclear interactions. But one of the nice things about the 20th century is we started to explore areas of physics outside of our everyday life. Relativity told us about what physics is like when we're moving very fast. Quantum mechanics when things are very small, and the nuclear interactions when things are even smaller. So this lecture is really a story about, well, the nuclear interactions. And that means we should start with radioactivity, and that brings us back to Becquerel, who was doing his experiments in the late 1800s. Becquerel was interested in phosphorescence, if I know my history right. I'm not a great historian of science, but he was interested in phosphorescence. He would take these mineral salts, and he would shine light on them. And after he shined light on them for a while, he'd take the light away and observe that they still glow. And, well, around the late 1800s, people discovered X-rays, and he thought maybe phosphorescence was related to X-rays. So he decided to perform an experiment where he'd take a bunch of mineral salts, he'd put them out in the bright light, let the light shine on them, and then after that he'd wrap them up in some photographic paper. And it was known that X-rays would cause burn marks on the photographic paper, and so he'd be able to see if his phosphorescence was also giving rise to some X-rays. And something funny happened when he went to do his experiment and went outside and there were clouds. So, it was a very cloudy, dark day. I think this is in Paris, I'm not totally sure. But it was very cloudy for several days, so he couldn't do his experiment, so he just took his mineral salts and he wrapped them in paper and put them aside anyway. And when he went back and opened up the paper, he discovered that the paper was burned even though the salts had never been exposed to sunlight. So the material in the salts was emitting some kind of radiation, even though it had never been exposed to sunlight. They were sort of naturally emitting radiation. And this was, the discovery of natural radioactivity. It was totally by accident. He was expecting to see radiation induced by, shining light on things. But, as luck would have it, weather was cloudy, so he, came across this process by accident. And that led to a Nobel Prize. Here, Marie Curie did many discoveries of radioactivity, discovered radioactive elements. The basic idea is that, well, you have some radioactive atom, and some process goes on in this atom, and that process will change the atom and cause some energy to be emitted, or maybe some particles to be emitted. And, well, as we know, this has had profound implications in all areas of life. So, after the discovery of radioactivity, it was sort of characterized, Ernest Rutherford characterized 3 different kinds of radioactivity. So if you have an atom here that emits some radiation, he characterized the distinct types of radiation according to what you needed to do in order to stop it. So if you have a particle that's emitting alpha rays, then a sheet of paper is enough to stop the radioactivity. If it's emitting beta rays, you need something more solid like aluminum, and if it's emitting gamma rays, you need a big block of lead. If you just put aluminum in front of a gamma ray, it's just going to shoot right through it. And we now know what these forms of radiation really are. Alpha rays are little helium nuclei, the little bundles of protons and neutrons. Beta rays are electrons, and gamma rays are just electromagnetic waves, which we know now, but they didn't know that. In this entire lecture, I put electrons in red. This entire lecture, we're really going to be focusing on beta decay as the driver of understanding the nuclear interactions. And Rutherford and Frederick Soddy, they discovered that beta decay does something very interesting. So I picked a particular beta decay process here, and I did it on purpose, of a radioactive cobalt atom, so that they can decay by beta decay to nickel. So I've drawn here, I reproduced here the periodic table of elements just to emphasize that cobalt and nickel are next to each other, and the process of decay actually makes cobalt transmute into nickel. It changes the form of the element. And so what these numbers here mean, just to remind you, I think I wrote it down here. Just to remind you that the top number is the number of protons plus neutrons in the element, and the bottom number is the number of protons. So you see the total number of nucleons is remaining unchanged, but the number of protons is jumping. And that's what's causing the type of the atom to be the same, or to change. And the way we understand this process is that some proton in the cobalt atom is, oops, I have this backwards. I'm very sorry, I fixed this almost everywhere, but I missed this one. It should be a neutron in the cobalt atom is decaying to a proton, plus an electron, plus, well, some other stuff. So what we're able to observe is we're able to observe that a neutron is decaying to a proton and an electron. And I couldn't help myself with this little sidebar that there is some other stuff here. And you can see there's some other stuff here in the following way, very indirectly. So when the cobalt atom decays to nickel and produces an electron, well, the cobalt atom is just sitting there. You just have a lattice of cobalt, a bunch of cobalt just sitting there. It decays, and after the decay, the nickel is just sitting there. So there's a difference between the mass of a cobalt atom and the mass of a nickel atom, and all of that mass should be carried away in energy of the electron. So it means that if this is really what's going on, the electron should come out with a fixed energy. But if you actually look and observe, the electron does not come out with a fixed energy. It comes with a varying spread of energies. And what that indicates is that, well, when the electron comes out with a low energy like this, where is the rest of the energy going? Something else has to be carrying that energy away. And this led to the discovery of a new particle, well, proposal of a new particle called the neutrino. So the neutrino was originally introduced just because in this interaction there was an energy mismatch. And, well, something had to be carrying that energy away, so Wolfgang Pauli said, well, there should be some neutral particle that doesn't interact very strongly with, it's very light, so there's no reason we would see it. It's neutral, it doesn't interact with electromagnetism, it's very light, so it barely interacts with gravity, so it's very hard for us to see it, but it must be there because it must be carrying some of the extra energy away. So Wolfgang Pauli actually called this thing the neutron. And, well, we now know neutron is the name we give to these things here that are sitting in the atom, or the nucleus of an atom. What happened was he called this the neutron, and then James Chadwick discovered this particle up here and called it the neutron. And so, okay, Fermi settled all this by saying, no, well, we should call this something else. We'll call it the neutrino. this is so Fermi was the first person that I know of to start putting the enos on the end of particles, and as we'll see,
you know why? You know why?
Because it's little.
Eno means more intelligent.
Yeah, exactly. Thank you.
Because he joked.
Yeah. So he was. So it's Italian. It's this Italian coming into the physics language, and as you'll see in the supersymmetry lecture, enos are everywhere. And it doesn't. And unfortunately, it doesn't mean small anymore. So the meaning's gotten confused. Basically, yeah, the super partner of any gauge field is an eno. So there are both enos and blue enos and weak enos and enos. And so you'll be sick of enos in 2 lectures. But I also put this famous picture of Fermi up here just for a reason, because this is the one that makes it on all the postage stamps, and this equation here is wrong. Everybody, we all joke about this in the group. You know, it's the Enrico Fermi Institute. We have pictures of Fermi everywhere. This picture, everybody jokes about it. If you look at the postage stamps, I didn't know this, but our colloquial speaker this week pointed it out. If you look at the postage stamps, they crop the photos so you only see the right-hand side of the equation. See, an equation is not wrong if you don't see what's on the left-hand side. Okay? So it's extremely clever, but physicists, we're not smart enough to do that cropping. We just use a big picture of the wrong equation. Anyway, no side comment. So I put Fermi up there because Fermi gave us the first good complete theory, a quantum theory describing this process of and I actually got it right here. That's good. This process of beta decay. He supposed there was some direct local interaction by which 4 fermions could talk to each other. A neutron would interact directly with an electron, proton, and neutrino. And actually, Fermi's theory is a little more than this, but he supposed there was a local interaction where these 4 fermions could talk to each other, and built a quantum theory out of that, and gave us the first sort of good model of the weak interactions at the quantum level. Now, just like electromagnetism, where a photon interacts with an electron, we have in electromagnetism there's a strength. There's an electric charge which tells us how strongly the electron couples to the photon. Well, there's also a number that has to tell us how strongly the neutron couples to the proton, electron, or neutrino. Or equivalently, a number that tells us sort of how fast this decay happens, at what rate does it happen. And that number is a number that goes by the name of GF. We call it the Fermi Constant. And it's effectively the interaction strength of the weak interactions. And I wanted to talk about GF because it has a very interesting property. It's the interesting property that, well, I put this combination GF over h bar c cubed. It's this interesting property that it carries mass dimension. If I write it sort of in these natural units in terms of h bar and c, it's not just a number. It's actually an energy scale that appears here, this giga electron volts. So I do this as an excuse to move into what we call the sort of natural units. In the rest of the lecture series, we'll be using these units because it's what we use in particle physics. And they're units where we basically set Planck's constant to the speed of light to 1. What does that mean? Well, the speed of light is just telling us how fast light is going. I can imagine that instead of measuring time in seconds, I can introduce my favorite, my own favorite unit of time. This is a Compton lecture, so I'll call it the Compton second. And I just define a Compton second is how long it takes light to move 1 meter. Okay? And if I measure time in Compton seconds, then the speed of light is 1, because it takes light 1 Compton second to move 1 meter. And similarly, you could adjust how you measure energies in order to make sure that h bar, the Planck's constant, is 1. And you can ignore the fact there's a bar here and not here. I put that there for people to know. There's a 2 pi hiding in here. Physicists often also work in units where we set 2 pi equals to 1, which makes no sense. But okay, we'll just do that. And in these natural units where h is c equals 1, you see this relation from last week where the energy of a quantum goes like 1 over the wavelength, really becomes, these factors just go away, energy is 1 over wavelength. And so there really is a very strict sense in which energy scales are like 1 over distance scales. And if I look at the Fermi constant in these units is 1 over 300 GeV, or is a distance scale, which is very, very small, 10 to the minus 16 centimeters squared. And by comparison, the electromagnetic interaction is just a number. So that's one thing that makes the weak interaction very different from electromagnetism. The weak interaction strength is parametrized by something that carries a dimension. It carries a characteristic length scale. There is a length scale associated with the weak interaction. And with the electromagnetic interaction, there is none. It's just a number. So it will, when we're talking, what this means is when we do experiments involving the weak interaction, things will depend on whether we are doing the experiment at energy scales smaller than this or larger than this. Whereas with electromagnetism, it doesn't matter what energy scale we're at, it's, in some sense the same. And just to give you an idea of what these units mean, a proton, you can think about a GeV is basically like the mass of a proton. So 300 GeV is like 300 times the proton mass. And this is the size of a proton, about 10 to the minus 13 centimeters. So, as I was saying, the electromagnetic interaction has no characteristic length or energy scale. It's just a number. And that reflects the fact that it's a long-range force. If I have a charged particle on the other side of the room and a charged particle here and I let them go, they're going to attract each other even at a long distance. But the Fermi interaction has a characteristic energy scale, or a characteristic distance scale. And that characteristic energy scale tells us roughly the distance over which the force is felt. The Fermi interaction is a short-range force. If we look at distance scales shorter than this, or energy scales larger than this, then we're sensitive to the Fermi interaction. But at distance scales larger than this, we're not sensitive to the Fermi interaction. So this is the sort of reasoning physicists often use when talking about sort of coupling constants and their dimensionality. So the other thing that's suggestive about this, when the coupling constant of your theory has dimension, when it has a characteristic energy scale, it also suggests that something funny might be happening at that energy scale. Again, because it looks, it looks different than whether you're small or large relative to that energy scale. And we'll see in a very real sense what this funny business is, and we'll see in a very specific sense why this force is short range versus long range. This is all just sort of guessing from dimensional analysis, but we'll see it more carefully later. So that's a little brief discussion of weak nuclear force, which is basically just telling us about the decay process that drives beta decay. And now I'll say quantum electrodynamics works perfectly well with a Higgs boson, but this force doesn't. And that's why we're going to need to introduce the Higgs. And in the rest of the lecture, except for the end part where I hope to talk a little bit about the LHC, I want to focus on two puzzles associated with the weak force. Two things that are very odd about it. One is parity violation, or you can think of as problems with mirrors. And the other is unitarity violation, which you can think of as problems with probability. So that's what we're going to be doing the rest of the time. So I want to start with parity violation, or problems with mirrors. Oh, good. Parity is, so what is parity? Parity is essentially a symmetry that reflects left and right. The statement that, left and right, what is left-handed, what is right-handed is kind of arbitrary, it's kind of off the bus. Physics shouldn't care so much about, whether something is left or right. So for years, people assumed that our world respected parity, which is to say, if you consider our real world, where Madame Wu here is looking to the right, and that's who this is, we'll talk more about her later, where she's looking to the right. If you look at the real world where she's looking to the right and do an experiment, well, then you consider doing a different experiment. It's a mirror world where just right and left have been interchanged. Then these two experiments should look the same. They should look the same. They should respect this flipping of left and right. So you should think the physics and laws of physics don't distinguish right from left. And this seems totally obvious that this should be the case, right? Because it's completely intuitive. And this is a great story, great example of something that happens in physics where there's something that seems very intuitive until you sit down and really think about how sure we are that we know what we think we know. So another example is this story of large extra dimensions that happened in the early 2000s. People toyed with the idea that our universe could have extra dimensions that are as big as a millimeter. And, you might think, wow, that's completely crazy. But, some people, including Nimar Kaniamed, they went and they looked at the experimental literature and asked, well, how sensitive, are there any experiments that have been done that could have seen evidence of this large extra dimension? And the answer is, unintuitively, no. So they proposed a bunch of experiments, and people did them, and of course they didn't find any evidence of that. These fifth force experiments came out of that. But Li and Yang did something very similar to that in the 1950s. They said parity seems like there's an obvious symmetry. nature shouldn't distinguish left from right, but how sure are we that we know what we think we know? And they looked back at the experimental literature, and they saw that a lot of experiments had been done to say, yes, electromagnetism doesn't distinguish left from right. You know, gravity doesn't distinguish left from right, but they pointed out that no experiment had really looked carefully at whether the weak interaction distinguished left from right. So I hope I have this year right, in 1956 they pointed out that parity of the weak interactions had been strongly tested and suggested a bunch of tests. Now a lot of people doubted that parity could be violated, and quite famously Richard Feynman bet one of his friends $50 that it's not. And of course the punchline is he lost his bet, so even people like Feynman can be wrong from time to time. Although I understand convincing him that he was wrong was quite a trick. See, in this business, you know, being right is one thing, but convincing other people that you're right is a whole other thing. So Lee and Yang suggested several experimental tests, and those experimental tests use the fact that parity flips the spin of a particle. So I can imagine I have a particle, and I'm drawing it really big, and it's spinning around like this. You know, the back is moving this way, and it's spinning around like this. And I draw this vector here because it's usually, you know, it's kind of clumsy to talk about what direction the spin is. Like if I say clockwise or counterclockwise, I have to say whether I'm looking from above or below. So what we do is, we teach undergraduates you should take your fingers and curl them up along the direction of the spinning, and then your thumb points in some direction, and that's the direction of the spin. So you curl your fingers around this direction and your thumb of your right hand, and your thumb points up, and so you draw a direction, and then you say, okay, it's spin up. And this particle, you would say, okay, it's spinning the other way, so I curl my fingers the other way, and my thumb is pointing down, so this one is spin down. So that gives us a way to talk about spins. And it's kind of funny, this right-hand rule, probably a lot of you know, you look at electromagnetism lecture halls while students are taking exams, you see them doing all this stuff. You have to get those directions right, because that's where you're going to lose points. Parity flips the spin of a particle. You know, if the part of the particle moving closest to us is going right, then in a mirror world, when I flip left and right, then it's going left. So, yeah, hopefully that's clear. The particle is spinning this way. In a mirror world, where I just interchange left and right, it's spinning the other direction. So it flips the spin of the particle.
We cannot think this doesn't seem to be correct.
Did I mess it up?
I think so. But
No, I think
anyway,
no, I think it's right. I think
Turn
it's
the right
right.
hand over, if you turn it right there.
yeah.
If you turn it up, it'll be the same.
Yeah, I think it's right. I think it's right.
And some time.
So parity, okay, so here's the experiment they proposed. By the way, they proposed several experiments, and you would think, you know, people believe so strongly in parity, there was not a rush to do them at all. They went to, she's referred to as Madame Wu, they went to her, she was a colleague of Lee and Yang at Columbia, and they convinced her to do this experiment, and you know, she was an expert in this cobalt stuff. And she did. And the idea was to, I think my laser pointer is done. The idea was to take a bunch of spinning cobalt nuclei and use the fact that the beta decay, the electrons that are emitted by radioactive cobalt nuclei tend to do so along the axis of the spin. So they tend to go up, they tend to come up going up, or come off going up, or come off going down. And what these guys said is they said, Lee and Yang said, if parity is preserved by the weak interactions, which is by this decay process, if parity is preserved by the weak interactions, then you should see the same number of electrons going up as going down. Why is that? Because in the mirror world, the spin is flipped. So if more electrons were going up, then along the direction of the spin, then in the mirror world, more electrons would go down. But you know, in the mirror world, the number of electrons coming out here should be the same as the number of electrons coming out here. So if this is supposed to be the same as this, but this is supposed to be the same as this, then they all have to be the same, so everybody has to be the same. So you should see the same number going up and down. And this will become more clear when I say what the results of the experiment actually were. The results of the experiment were, some electrons went up, but a whole lot more went down. Now, this is a very tricky experiment to do. You have to, you know, in order to do this experiment, you need a big sample of cobalt where all the spins are aligned. So you have to use a magnetic field to align them at the beginning. But then you have to cool the cobalt nuclei a whole lot, because if there's any temperature in the material at all, then the random vibrations from that temperature are going to cause the spins to flip back and So it was a very difficult experiment to do. Yeah. So she saw more coming down, and so that tells us that in the left-right world, well, okay, weak interactions always say that more electrons come out against the spin. So if this particle is spinning down, then more electrons will come out going up, right? So, you know, she saw in her experiment the electrons like to come out in the direction opposite the spin. So, okay, if I flip the spin of the particle, then more electrons will go up than down. But now this situation is not left-right symmetric. If I flip left and right, I flip the spin of the particle. But in the real world, I saw tons of electrons down here. And in the mirror world, I don't see many at all. So I get, you know, different results in the real and mirror worlds. Yeah, and I apologize, in the handout I have this flipped over because there's many ways you can explain this, and I changed my mind last night talking about it to explain it. But you know, the idea is clear. You know, in the mirror world, you just see, you know, a different experimental result than you do in the real world. So the weak interactions can tell the difference between right and left, and this led to one of the fastest Nobel Prizes, I think, ever. Because these guys put out their paper in 56, if I have my years right. It was early 56. Madame finished her experiment at the end of 56 and reported in 57, and there was a paper that came out right after hers. There's some story where she found, this is kind of interesting, she found a positive result, and she told these guys about it. But she said, look, we're not done yet. We have to do some extra checking in the experiment, so don't tell anybody. And so, of course, they went and told people. They went to this Friday, whatever, lunch meeting in Columbia, and they told people, and there were some accelerator physicists there, and the accelerator physicist said, aha, you know, we can't do this cobalt test, but there was another accelerator test they could do. They went and did it real fast, and they found, oh yeah, parity violated, and but they very politely waited for Madame's experiment to finish and put their paper out after. So, two experiments, this is the way physics is supposed to go. You know, people are supposed to have this, doesn't always work this way. But, you know, these two papers, they appeared at the beginning of 57, and I think the Nobel Prize was awarded that year, which is really fast. But this is paradigm altering, and two totally different experiments, came in and verified. It's paradigm altering. The weak interactions can tell the right from the left. It's totally weird.
Is there an issue that she wasn't in on the Nobel Prize?
There may have been. I'm not a good historian of this, but it is true. I don't think she ever won a Nobel Prize. Yeah, I'm unfortunately not so educated on this type of history. So I wanted to be more specific about exactly how the weak interactions tell right from left. So I thought I should be more specific about what we think of, how we think of right and left in particle physics. So the way we think of right and left in particle physics, for a particle, a spinning particle, has to do with its momentum relative to its spin. So if I have a particle that's spinning up and the momentum is down, you know, the momentum of a particle is moving in the opposite direction of its spin, then I say it's left-handed. And if it's moving in the same direction as its spin, then I say it's right-handed. And as a lefty, I'm going to say that this convention must have come out because people think that this looks odd and weird, and so I take it as kind of an affronting that's left-handed. People, you know, this is sort of more natural, they're aligned, okay. So this is right-handed, this is left-handed, but okay. And the statement about the weak interactions is that weak interactions, when I wrote this for Fermi interaction, weak interactions involve only left-handed particles. They do not involve right-handed particles. So if a particle is moving in the same direction as its spin, it doesn't undergo weak decays. But if it's moving in the opposite direction as its spin, then it can. Now, why is this a problem? This is a problem because if you have a massive particle, the handedness depends on the observer. So I can imagine I have a particle, it's spinning, and its spin is this way, and it's moving this way. So I would say it's left-handed. And now I think about somebody in a race car. You know, maybe you're in a race car. You know, driving real fast. If you're going fast enough, then me standing over here, I think the particle's going to the right. But if you're moving fast enough, if you're moving faster than the particle, you will think it's going to the left. Which means I'm going to look at this particle, and I'm going to say this is a left-handed particle. It can undergo weak decays. You will look at the particle, and you will say this is a right-handed particle. It cannot undergo weak decays. And that's a horrible, horrible contradiction. So standing on the side, I think that the left-handed particle participates in the weak interactions. But you're looking at the same particle, but you're looking at it from a car, and you say, oh, no, it shouldn't participate in the weak interaction. It makes no sense. Now, why did I assume massive here? I had to write massive here because a massless particle doesn't have this problem. A massless particle moves at the speed of light. And as we saw in the first lecture, Nothing moves faster than the speed of light. So if we drive along in our car, we can put the pedal to the metal as much as we want. We're never going to pass the particle. We're never going to be going faster than the particle. So we will always see the particle moving to the right. We can never catch up to it. So because we can never catch up to it, people from the car will always see left-handed, just like the observers will always see left-handed. So everybody will agree that a massless particle is left-handed. So just to summarize the parity puzzle, massless particles can be right-handed, where their spin is aligned with their direction of motion, or left-handed, where their spin is anti-aligned with their direction of motion. A massive particle can have either handedness depending on who's looking at it. So handedness is not an invariant thing for a massive particle. It depends on your vantage point, your reference frame. But we know that the weak interaction couples only to left-handed particles and not to right-handed particles. So in order to avoid this contradiction, that tells us that at some level all particles have to be fundamentally massless. And this, in a sense, is one of the reasons why we need Higgs boson. Incidentally, it's not the reason. It's not the main thing that Higgs and the company were really studying. But this is essentially one of the reasons that we need a Higgs boson.
Well, why does momentum and spin have to be in parallel directions? Why can't they be oblique to each other?
Good. So when I'm talking about spin here, when a particle, the spin of a particle always depends on the measurement. So what I mean by this is, suppose I measure this. I can try to measure the component of the spin of the particle in any direction that I want. So what this statement is really saying, good question, thank you. What this statement is really saying is if I measure the spin of the particle in the direction of its motion, then I will find that it's either, that part of the spin is either going up or down. So it will have an uncertain spin in other directions. I didn't talk about quantum spins there. It will have an uncertain spin in other directions. So what I'm referring to here is the component of the spin that's parallel in the direction of the momentum. And when I measure it, it will either be up or down. Does that answer your question? Maybe you want to say something.
The only way you get a vector direction.
Yeah. So yeah, in principle, I could measure the spin of the particle. Like I could do a measurement of what is the spin of the particle in this direction if I wanted to. But how do I want to say? That wouldn't be an invariant quantity. So then there's this. Wait, how can everything be massless? Because an electron has a mass. What happens? So how do you generate mass? And well, here's an idea how you can do it. You start with a massless right-handed particle that you call an electron, and a massless left-handed particle that you call a left-handed electron. And you just add some new field. You call it a Higgs field that couples to them. The idea is that a left-handed electron, as it moves along, if it encounters a Higgs field, or encounters a Higgs particle, then it can interact with it and produce a right-handed electron. And this arrow should be going the other way. I'll fix that on the slide. So electrons can acquire a mass if the vacuum has a bath of these Higgs fields. If you imagine there's like a sort of Higgs bath, there's Higgs particles everywhere, then as an electron moves around in this bath, it will constantly be bouncing off of Higgs fields all the time. And the way you can think about this Higgs bath is, well, it's kind of similar to an electric field. If I was talking before about how you can think of a constant electric field. Imagine a constant electric field permeating all of space. If I have a constant electric field permeating all of space, I can think of that as sort of a large ensemble of photons, where, okay, now if a charged particle that moves in this electric field is constantly going to be influenced. Its motion will constantly be influenced by the electric field. And at the quantum level, we can think about that as follows. We can think we have a bath of photons, and as the particle moves along in the bath, it's constantly scattering off of all the photons in the bath. It's just, constantly interacting with them. This is the same kind of thing. It's like turning on a background field sort of everywhere in space. And the Higgs boson is a small fluctuation of this field. Now, CERN has a really wonderful cartoon description of this that I decided I would put up here. Maybe you've seen before, if you've seen popular talks on the Higgs, you've seen this many times in coaching myself. You can think of the Higgs bath as like some crowded room of physicists. There's a bunch of physicists in a room mulling around, and okay, that's like the sort of Higgs bath in the vacuum. Then you imagine that Einstein walks in, and as soon as Einstein walks in, everybody wants to talk to him. So Einstein's trying to walk through the room, but all the physicists sort of gather around him and ask him tons of questions, and it really slows him down, and he sort of has this bubble of people around him constantly slowing his motion as he tries to move through the room. So Einstein is like a particle coming along, trying to move through this Higgs bath. And the people crowding around Einstein, slowing him down, is effectively describing how that particle is gaining mass. Now, there's another version of this cartoon where instead of Einstein, you have somebody less important like me walking in the room, and then you're not going to have this big bubble. Maybe just 2 or 3 people want to talk to me. So that means I'll be able to go faster through the room. So that gives you an idea of how particular particles get different mass. Einstein will be much more massive than me because he will attract a much bigger bubble of people and move a lot slower. If I come in, I'll be able to move quite a bit faster, maybe close to the speed of light. So what about the Higgs boson? Well, the Higgs boson itself, you can think of as this. The Higgs boson is just a small excitation of the background field, and you can think of it this way. Somebody shouts a rumor into the room like, oh, hey, they discovered the Higgs at CERN, and everybody gets excited. Well, I should say something. I wrote small excitation, so I shouldn't say somebody discovers the Higgs, because that's a big excitation. CERN ruled out some model. Okay, so that's a small excitation, but everybody wants to know about it, so people gather in little groups and talk about it, and the rumor spreads through the room. And physicists cluster around little clusters as the rumor passes through the room. And this excitation through the room is kind of like a Higgs boson. It's a small excitation of the background field that propagates on its own in the room. So that's CERN's very nice cartoon description of the Higgs boson, which I tend to like a lot.
But that doesn't count for inertia, though. I mean,
No, at a very fundamental level, it gives the particle the exact equivalent of a mass. In the sense that if you look at low energy scales, low enough energy scales, it's indistinct, like below this 300 GeV, it's indistinguishable from having a mass. Completely indistinguishable. Yeah. So here's the resolution of the parity puzzle. Massless charged particles can be right-handed or they can be left-handed. Pairs of massless particles can become massive by interacting with each other through this Higgs bath. And the weak forces allow them to violate parity. You could have asked, well, how does this address this problem that the weak interactions violate parity and deal with right and left differently? And what allows that is this Higgs field carries weak charge. This Higgs field couples to weak interactions. So you can think of a right-handed particle as sort of similar to a left-handed, you can think of a left-handed particle as sort of similar to a right-handed particle and a Higgs boson. And so, some next stage of Higgs field. And so the right-handed particle doesn't couple to weak interactions, but the Higgs does, and that's how the left-handed ties into the couple. So this solution requires a new fundamental scalar particle, and that new fundamental scalar particle is the Higgs boson. Now, it's important to point out that Higgs is not the only person who did the work on the Higgs boson. He just got his name on it. There are actually 6 people, and there is a long history. There's a detailed history. If you look on Wikipedia, and I said, and Goralnik wrote, I think, a 30-page paper that just describes the history of the discovery of the Higgs mechanism. There are 3 papers, 6 authors, all of whom, and Higgs wasn't the first, he was the second. And in some sense, I'm told by people who study this more carefully than me that the 3rd paper actually gets more of the details right. I don't know. There's a big. When they find the Higgs, the Nobel Prize Committee is going to have a big problem on its hands because it can only give 3 prizes at a time. And it might have to give 2 theory prizes for the Higgs because if any of these people get left out, there's going to be, and there's some nationalist stuff going on too because there's some French and then British. So there's so much politics in this. I don't know any of it. The only thing I do know, it's unfortunate. Robert Brown passed away last year, so he will not be getting a Nobel Prize, which is sad. And but other than that, there's some horrible political stuff going on around here. I don't even know it, but if you're interested, you just look on Wikipedia. There's a big story. And if you see talks, I've seen some CDF talks, and they'll not refer to this as the Higgs mechanism, but some concatenation of all of these guys' names, which is unpronounceable. Okay, so that's the first part, which is about parity violation and problems with mirrors. The second part of the talk, I want to talk about the other reason we need a Higgs, which is actually in some sense more, the thing that people were really worried about at the time, which is unitarity violation or problems with probabilities. So we come back to Fermi's theory and the long equation up here in the corner. We come back to Fermi's theory, and Fermi's theory, which has this interaction strength that sets an energy scale. And now I want to say a little bit more about what goes wrong with Fermi's theory if we do scattering experiments and energy much beyond this energy scale. Now I'm going to just give a very rough description. Fermi's theory is badly behaved because it violates what we call unitarity. And unitarity is a bedrock principle in particle physics. Unitarity is basically the statement, is the following statement. If I set up an experiment and I do it, and I think about everything that could possibly happen, and I calculate the probability of everything that could possibly happen, and I add all those probabilities together, the answer better be 1. Because with probability 100%, something happens. We don't know what, but something happens. So if you sum all the probabilities, then everything should sum to 1. If your probabilities don't sum to 1, then you're not really calculating probabilities. You're doing some nonsense, and you have to think very hard. And by the way, it's not uncommon for computations in field theory to give you garbage answers. And when it gives you garbage answers, the theory is always smarter than you are. So if it gives you garbage answers, it means you're doing something wrong, and you need to think very carefully. So Fermi's theory starts violating this condition for experiments and energies that are a little beyond 300 giga-electron volts. And sort of a rough way of understanding this is the following. And this is very rough. I should have a cross-section here. And there's optical theorem hiding here for people who are experts. So I apologize for that. But very roughly, if I calculate the probability of say, a neutron scattering off a neutrino, so I've reordered the diagram a little bit here, but I imagine the neutron scatters off a neutrino in order to make an electron and a proton. It's the same diagram I wrote before. I've just moved the neutrino around in the initial state. And if I look at sort of the probability of this scattering process happening, well, it has to have a factor of this Fermi constant, because this Fermi constant tells me how strong the interaction is. But this Fermi constant has dimensions of 1 over energy squared. Probability has is dimensionless. It's just a number. So it means that I have to put an energy here in order to make it dimensionless. So I have to have some E squared. What is this energy? Well, this energy is going to be the initial center of mass energy that I'm doing the experiment at. And so the probability, because the Fermi constant grows with, or has this sort of energy dependence in it, I'm forced, no matter how, I'm going to do the calculation, but I can tell, even before I do the calculation, that the probability is going to grow dramatically in energy. This is an example of using dimensional analysis to get a handle on what the result of your calculation is going to be before you even do the calculation. And if the probability of this sort of scattering process grows with energy like this, well, when energy is very small, this is kind of a small number. But if the energy becomes very large, this becomes huge. And at some point, there's a numerical factor here I didn't put because you have to do some calculation. But at some point, this thing in the parentheses is going to be much bigger than the numerical factor. And I'm going to get probabilities that are just growing wildly out of control. And you can see the 300 GeV is entering because 300 GeV is the difference between this number being large and this number being small. So if the energy is much bigger than 300, so what tells you you're in trouble is when this energy is much bigger than 300 GeV. And if you do it correctly, I think that Fermi's theory starts running into problems with unitarity around 500 GeV, which is essentially the same. So Fermi's theory is not a good fundamental theory. It's only an effective theory which describes physics and energies lower than this 300 GeV. New physics has to appear before we get much beyond that energy scale. And this gives me an excuse to introduce this naturalist principle. The naturalist principle says, well, new physics has to come in at least below 300 GeV, but since 300 GeV is the number in the problem, well, we would expect that the new physics actually appears pretty close to 300 GeV. And it turns out that's right. At high energies, you discover, and people discovered this at CERN, I'll say more about it later, you discover that Fermi's interaction at high energies is really this in disguise. The scattering of a neutron and proton off of an electron, or into an electron or neutrino is mediated by the exchange of a heavy particle. So the neutron doesn't just spontaneously become a proton, electron, or neutrino, but it becomes a proton in this intermediate particle called a W. The W propagates along for a while, and then it decays. And this W mass represents the new physics that we knew had to enter below 300 GeV to solve this unitarity problem. And the W mass is about 80 GeV, and you'll see this isn't too far from 300 GeV. It's a factor of between 3 and 4. To a particle physicist, that's basically 1. So okay. Yeah. This is right. So it's mediated by the exchange of this heavy particle. Now, why were we able to use this so successfully for a while? Well, this is a heavy particle that decays, and well, it decays after some time, and if you're at very low energies, it doesn't have a chance to move very far before it decays. So you can imagine if I do an experiment where the neutron comes in with very low energy, the W is going to move a little bit and then decay, and if the distance the W travels is short enough, then you can't even really tell it was there. It sort of looks point-like. A rough idea. So in reality, we don't get one heavy new particle, we actually get three. I thought I had put this up here. There's a thing called the W minus. If you rotate things around, there's a W plus. There's a thing called the Z particle. The Z is a little bit heavier. It's 91 GeV. That's not important. The important thing is that these intermediate particles, they're very close analogs of the photon. They're just like the photon in electromagnetism, except they're massive. And that mass sets a distance scale, because we know that the mass scales and length scales are the same. That mass sets a distance scale, which tells us how far that force is felt. So just to give a comparison, this is what a similar diagram would look like in electromagnetism. In electromagnetism, we would describe two electrons interacting with each other. Electrons, they're charged particles, so they exert forces on each other. And at particle physics level, that happens because they exchange a photon. And here you have a neutron, say, interacting with a neutrino because it exchanges a Z. And the difference, again, is a photon's a massless particle that's stable. So this particle can propagate for as long as you want. So I can move these electrons way out here, and they would still talk to each other because the photon could still make it out. The Z is an unstable massive particle. So if the neutron's too far away, then this Z will just decay into other stuff before it ever gets to the neutron. So the force mediated by the massive particle, by the Z, is a short-range force as opposed to a long-range force. So I wanted to put this up. The W and Z bosons were discovered at CERN in 1983. There was a Nobel Prize for it. These UA1 and UA2 experiments. And I just wanted to take this as an excuse to put up a picture of the accelerator complex at CERN because there's a lot of stuff going on here. I don't even know half of this stuff. A ton of crazy stuff. Here's the neutrino beam that goes off the opera so they can think they see a little bit of neutrinos. Here's the LHC ring. And the cute thing is the collider that they used to discover the W and Z bosons back then is now one of the injectors for the main LHC ring. So the collider they used back then was this little thing. And now they're just using this as a precursor. They accelerate particles around here and then throw them into the bigger ring, which is the LHC, where they're colliding photons. So here's an example of what the discovery data looks like for a W and Z. They discovered that the SPS was a proton-antiproton collider. So they take protons, make them go real fast, and antiprotons, make them go real fast, and smash them together. And well, what happens, you get the proton and antiproton, or more correctly, a quark and antiquark. They'll produce one of these W particles. It'll live for a while, and then it'll decay to an electron and a neutrino. And what you do is you look at the spectrum of these electrons. And so here's a spectrum, and here's the energy of the electron, and how many they actually see. And you look at the spectrum of these electrons, and then you can do some calculation for what it should be depending on the W mass, and you can read it off from that. So these W and Z particles, they really are there, and you can actually see them in accelerator experiments. Now, the Higgs comes in because it's difficult to quantize, it's difficult to describe quantum mechanically massive analogs of the photon. So to get an idea of why, I want to go back to our old friend, the electromagnetic wave, which again, remember, we think of as sort of an ensemble of photons. This electromagnetic wave actually has two different polarizations, two sort of states that it can be in. If I think about an electromagnetic wave moving through space, the electric field can oscillate up and down, or it can oscillate from side to side. It's sort of two different states, and this is a classical way of seeing something that is quantum mechanical, which is that the photon has two distinct energy states. Now, in principle, there could have been a third polarization, and this is how sound waves work. You can have a polarization that looks like this, like a bunch on a slinky sort of moving down. You bunch up a bit of a slinky and let it go, and that little bunch will propagate along. And the way this works is some parts of the slinky are moving faster than others, and that variation in the speed at which they're moving gives another sort of wave component. So there's some lump that propagates. And it's kind of like a polarization that's along the direction of motion. Now, light can't do this because every part of a light wave moves at a fixed speed, moves at the speed of light, so nothing can go faster. But if you have a wave made from massive force carriers, then it absolutely could do it. a massive particle sometimes can move fast, or so you can have something where the speeds are varying, and you get some sort of lump where there's a lot of them here and not as many here, and that lump just moves along. This is my sort of fast-hand way of trying to say something which is a little bit which is a little more fundamental, and that is that while a massless force carrier has 2 degrees of freedom, a massive force carrier has 3. So it's a very fundamental difference, and this 3rd degree of freedom causes a lot of problems. Other differences, the massless force carrier is a long-range force. As I said before, the electromagnetic coupling has no energy scale in it at all. The photon is perfectly stable. These guys can emit a photon, and it's free to interact with any other electron up here, or the other side of the solar system. It's free to do that, so the force can be felt across very long distances. This is a short-range force. The mass of the W and Z tells us roughly how long it will travel before it decays. So if I have a neutron coming along and emits a W boson, it will not propagate forever. It will propagate a certain distance and then decay. So if I want the force to be felt at long distances, then I need to start off with enough energy that the W travels very far before it decays. At low energies, the W won't travel very far, and so this puts a cap on how far the force is felt. And that's also why we don't see these forces outside of nuclear distance scales. They're felt at nuclear distance scales, but not beyond. So coming back to this extra degree of freedom, this extra degree of freedom can cause more problems with unitarity, more problems with probability in the Compton theory. And I'm just going to say what those problems are. I'm sorry I have to wave hands a little bit. But if you try to do an experiment like, for example, WW scattering, you take 2 of these W bosons and shoot them at each other and see what happens. This experiment, this set of diagrams will cause problems. With unitarity and cause divergences. And those divergences come from propagation of this extra longitudinal mode, this extra degree of freedom. So this is a fundamental problem that says even this theory of massive vector bosons. So we started with Fermi's theory. That had problems with unitarity. We said, okay, if you look closely, then there are extra, this force is really coming from the exchange of a massive particle. But that behaves badly, so what the heck? These behave badly around a tera-electron volt, which is 1,000 giga-electron volts. And the idea is that, well, the W and Z should be fundamentally massless, just like the photon. We have no problem with the photon. And then they acquire their mass the same way that those other charged particles did, in that they get their mass from this bath of Higgs fields. And this can be done in such a way that you can cure all these problems. Now, this is a bit of a difficulty, and I introduced all this because this is one of the things that Higgs and these guys really developed. The W and Z are fundamentally massless. You give them their mass from the Higgs bath, but I said before, a massless photon has 2 degrees of freedom. A massive one has 3. So this extra degree of freedom that's causing all these problems has to come from somewhere. And the statement is it comes from the Higgs particle itself. So I felt obliged to draw this Mexican hat potential just because every talk on the Higgs does. I'm not going to say much about it, other than you can imagine that this ball is telling us sort of what the value of the Higgs field is everywhere in space. And this is at every point in space. And this potential is telling us the energy associated with the Higgs field at every point in space. So you can imagine one copy of this potential at every point in space. And the fact that it's inverted says the Higgs field doesn't want to be 0. The Higgs field wants to take a value that's down here, where the energy is lower. And well, there's also many directions the Higgs field can move. You can imagine wiggling the Higgs field this way, and it happens that this gives you the extra degrees of freedom for the W and Z. Or you can wiggle it this way, roughly speaking, that gives you the degrees of freedom the Higgs boson. I didn't have time, the proper discussion of this figure. It takes some time, I apologize. But the main takeaway point is that there's some natural potential which drives the Higgs field to be non-zero, creating this Higgs bath that everything is mass from, and that there's a natural description in this picture of the extra degrees of freedom that we need to make the W and Z particles heavy. So, and this Higgs particle, once we have it, it cures this problem of scattering by giving us new diagrams, and these diagrams cancel the divergences and bad things of these diagrams to make sure that WW scattering is better behaved. So the takeaway point from this slide is that without something like the Higgs, without these extra diagrams, the standard model of particle physics would violate unitarity around a TeV scale. And this is why everybody says that the LHC must see something like the Higgs. It has to see the Higgs or something like it, because the standard model by itself just breaks. It breaks. You calculate probabilities, you find probabilities don't sum to 1. So the things you're calling probabilities aren't probabilities. The theory completely breaks. So something like the Higgs has to be there. And that's why when they weren't seeing anything, we were all getting very worried. We were all very happy that they are seeing things. So to summarize the two puzzles, and I put this one first because I thought this one was a little bit cleaner. One puzzle was the problem with mirrors, and that problem said that you couldn't have massive particles, but we got mass by interacting with this Higgs bath. The second puzzle was this long digression on problems with probabilities. That's the statement that Fermi's theory breaks down at higher energies, requires massive force carrier particles, and there are a lot of problems associated with giving mass to force carrier particles, but the Higgs, in some way that I unfortunately just had to wave my hands through, but the Higgs actually does solve all of those problems. So the Higgs actually solves two problems of mass. It gives mass to ordinary particles, and it gives mass to the carriers of the weak nuclear force. And, well, I felt obliged to put this slide up just to say that actually there's a nice geometric picture where you can put the photon and the weak bosons all in some matrices, and these matrices actually have a deep meaning. These matrices tell us there's some sort of unified symmetry that's describing simultaneously electromagnetism and the weak interactions. This goes under the name of the Electroweak Theory. This is the next step towards grand unification of understanding all of physics with one theory. And this beautiful theory earned these guys the Nobel Prize. And this is now my excuse to tell the story I really love about Steven Weinberg. Steven Weinberg was a professor at Harvard, and he got hired away by University of Texas at Austin, where he is today. But he thought that UT Austin had too much of an emphasis on the football program. So he demanded, as part of his package, he demanded to be paid $1 more than the football coach. Now, the mistake here is I don't think he made it retroactive. So, or I'm sorry, made it retroactive. The mistake here is I think it was like paid $1 more than the football coach on that day. I imagine that it was something that was consistently updated, that when Texas was in the national championship game some years ago, nobody's rooting harder than Steven Weinberg. Guaranteed raise for the football coach. I don't think that's how it works, but I really don't tell the story. So, yeah, a big loss for Harvard, of course. They've had their share of losses. So I'm basically out of time, so I had about 3 or 4 slides on looking for the Higgs. I will show these slides again next time, but I wanted to show, I just wanted to flash up the raw data of what Atlas and CMS are showing with this Higgs mover. They might be seeing a Higgs at 125 GeV, and I wanted to show this data because this is a trick I saw at a colloquium earlier this semester. I really thought it was cool. This is the axis of mass, and this is sort of the number of part events that you see as a function of what the Higgs mass is. And I wanted to say, can you see the signal in here? Can you see it in here? The CMS data, I can't see it at all. CMS, here you can sort of see it. And it's here. This is what all the excitement's about. It's this little blip right there. That's it. That's it. And well, when you do some subtraction, it becomes that. And they turn it into a plot like this, which I'll explain next time. And this big bump is why everybody's really excited. So I'll just put up my summary. Weak interactions violate parity. Nature distinguishes right and left. Massive particles can be left or right-handed. And so you shouldn't have any massive particles at fundamental level, but the Higgs solves all these problems, and then the Higgs solves these problems of unitarity and weak interaction. So I'll stop there, and I promise I will spend the first 15 minutes next time talking about Atlas and CMS looking for the Higgs and what they're doing in a more careful way. The question is, are there any other standard bosons? And the answer is no. The standard model has one for this answer. So we actually have not discovered any fundamental standards, though, because we haven't discovered any.